This is a brief video into how to perform integration. The material's already been covered in chapter 7, but I thought it would be nice to include it again separately in case you would like to refer back at any time and see how to integrate. Integration is a tool that we use in physics to calculate areas, and in fact it's a topic that you'll cover in great detail in maths. But for me it's interesting to just teach you a little bit about integration and give you the background so that you're able to use it as a tool for the physics that we want to do. So in this sheet what I have here is we're going to consider a function. So for example, the function might be 3x squared. And then we know what we can do is, we can differentiate the function, right? And we're all familiar with how to differentiate a function. We simply take the 2 and we multiply it by the 3. It gives us 6, and then we decrease the power by 1. But when we speak about integration, we're speaking about how do you go backwards. If you're already given a derivative, how do you go backwards and determine what the function is? In that sense, we might think of differentiation. We might think of it as an integration. We given some derivative and we want to go back. So how could we go back from 6x to 3x squared? Well, let's take a look at another example. If I'm given a derivative and the derivative is 18x squared as shown here, then the question is, how can I go back from this derivative and find the original function? And there's a little recipe that we follow which tells us how to go back and integrate, how to undifferentiate. So the rule that we take is we start by having the x, we take this power. At the moment the power is 2. The rule is that we raise the power by 1, so we increase it by 1. So if we go from 2 to increase 2 by 1 gives us 3. And then what we need to do is take this number in front and we need to divide it by the new power. So the new power that we found over here is 3. So this then gives us 18 divided by 3 is 6x to the 3. We can check if we've performed the integration correctly, and the very simple way for us to check is by differentiating this. If I differentiate this, it becomes 6 times 3 is 18 x squared. So this shows that we have performed the operation correctly. We've performed the integration correctly. Let's have a look at another example. If we want to take the function 36x to the power of 3 and we want to integrate that, then I start off by writing the x, and at this time the power is 3. So now remember, I need to increase this power by 1, so I change the 3 to a 4, and then I need to divide the number 36. I need to divide that by the new power. The new power is 4. And if we simplify this, then we can see 36 divided by 4 is equal to 9x to the power of 4. And if we differentiate 9x to the power of 4, we do indeed get 36 to the power of 3. So this goes to show that our integration has been successful. An interesting case we might have is if we have the number 5. So if we're given that the derivative of a graph is 5, and we asked to integrate that and find what the original function is, then at first that might seem a little bit confusing because we don't see an x there. But we can actually take this 5 and write it as 5x to the power of 0, because remember, anything to the power of 0 is 1. So by writing 5x to the power of 0, it's of course just 5. And if we integrate 5x to the power of 0 and we carry out the same rule, then the rule says we start with the x, we raise the power by 1, so we make this from 0 to 1, and then we take the number in front, we take the 5, and we divide it by the new power. So then this just gives us 5x. And we can see that basically, having done this, if we differentiate 5x, of course this just becomes 5. So that's again a way to check that we've done it correctly. If we have a function with multiple terms, as in here we have 26x plus 6, then we do it in exactly the same way, except we just do each of the terms individually. So when we deal with the 26, then at the moment it's 26x, so it's x to the power of 1, so we change this to x squared, and then we take our 26, we take our 26 and we divide it by the new power, so the new power is 2. Then we need to also take care of the second term. So remember, 6 is the same as 6x to the power of 0. So if I want to integrate x to the power of 0, then I make it x to the power of 1. And of course it's just going to be 6 divided by 1, which gives us the 6. So this then is equivalent to 13x squared plus 6x. And if we differentiate this, we get 26x plus 6, which shows that we've done our integration correctly. So then, in the next slide, we generalize this rule. We give, in this slide, the general mathematical notation. So if we have a function f prime of x, this is the derivative and it's written in this form, ax to the n. If we want to go back and we want to find out what the function itself is, so remember the function is just f of x, then the way we do that is we take the power of the derivative and we increase it by 1, so then we have x to the power of n plus 1, and the coefficients, we divide the a by the new power, so it's divided by n plus 1. So this statement here is just a general mathematical rule of writing out the recipe that we've been following to do our integration, to perform these steps. So we've been looking at integration and we've seen that there's a little rule or recipe that we follow to perform integration, but it's super important for us to remind ourselves of why we want to do integration and what we're hoping to achieve. And this is summarized in this picture here. So remember, when we deal with differentiation, differentiation refers to a gradient. So what I have here is some function f of x given by this varying black line. If I differentiate f of x, then I get f prime of x, which is a gradient at some point. If I differentiate, the opposite of differentiation is integration. And integration is a tool that we use to calculate an area under a curve. So if I wanted to calculate the area from between a and b under this curve f of x, under the curve f of x, then I would use integration to find this area. And the integral I would need to evaluate is the integral from a to b of f of x dx. So we've seen the rule, the recipe to follow for integration, but now it will be interesting for us just to look at an example to confirm that this recipe or this rule actually works and that integration works as we think it should. So here's an example then. Find the area under the curve between x equals to 0 and x equals to 3. So in this example, you can see what I have is a curve, and this curve is given by f of x is equal to 2x. And you can see it's f of x is equal to 2x because when x is 1, f of x or y is 2. When x is 2, f of x is 4, and so forth. But the problem we asked is to find the area under this curve between x equals 0, so from here, and x equals 3. So if we look at this, then this actually forms, a triangle. This forms a triangle. So the question is, find the area of this triangle, the area under the curve between x equals to 0 and x equals to 3. And what we're going to do is we're going to use first the conventional way to find the area of a triangle, and secondly we're going to use the integration method. And then we're going to compare the two answers we get, and hopefully we'll see the answers will be the same to show that our integration method works well. So a formula that we often use to find the area of a triangle, the area of a triangle is just half base times height. So for us the base is 3, so the area is going to be half times the base is this base here, the length is 3, and the height we can see is 6. So it's half 3 times 6, and this is equal to 9. So according to this conventional formula, the area of this triangle A is equal to 9. Now let's try use our integration tool and see if we can get the same answer. So here we've written this question in words. We've written it in integration formula. The area is equal to the integral from 0 to 3 of the function 2x in terms of dx. If we perform this integration, then what we're integrating is 2x, right? So the rule that we do is we take the x, and at the moment it's x to the power of 1, so we need to increase the power by 1, so we make that a 2, and then we take this old coefficients and we divide it by the new power, so divide by 2. And the notation that we use is we rewrite this integral sign and we say that this is over the domain from 0 to 3. So in the next step, what we can do is we can simply just simplify this expression inside the brackets. So this is just going to be x squared, and as x goes from 0 to 3. Now, the way we finish the problem, or the way we evaluate the problem, is we take this x squared and we substitute the top number, the 3, in. So this becomes 3 squared, and then we put a minus sign, and then we substitute the 0 in again. So wherever we see x, we put a 0. So this is just going to be 0 squared. And we can see that, 3 squared minus 0 squared is also 9. And what we see is that using both of the methods, we arrive at the answer 9. So this is a confirmation then that our integration tool, our integration recipe is working correctly, because it gives the correct answer. It gives us the answer that we were expecting. In the slides then there's another example we can look at. In this example we asked to integrate 9x squared, that's our function, between the limits of a and b. And the way we do that is, you know, as before, we take this power and we increase it to 1, so it becomes x to the power of 3, and then we take the 9 and we divide it by the new coefficient, and then we write the limits as shown. So this simplifies just to 3x to the power of 3, and this is between the integration bounds of b and a. As I've already said, the way we evaluate this is first, wherever we see a x, we substitute b in. So this becomes 3b to the power of 3. And then from that we subtract, you know, wherever we see an x, we put an a in. So it's minus 3a to the power of 3. And that's our solution. Right, so then this is a sufficient introduction to integration to show you how it works, to show you how the area under a curve can be calculated, and from now on we'll move forward and use this, apply it as a tool